kind of equations. In particular, this means that these ones are the unique solution, because the solution is unique, and you can check that these ones satisfy these equations, so it means that this one is the unique solution that we have. So that means that Tt, n of t, e of t, are orthonormal. For all times. Yes, if that was a bit like maybe confusing, it's, maybe that's not like the most essential part of the proof. The most essential part is like this idea of using these equations to define T, N, and B. And now we just checked that this implies in particular that they are orthonormal for all times. And now we have to still define the function and what we do, or like the curve. And for this, we use the fact that the t that we just found has to be the time derivative, the first derivative of the curve. So we can integrate this equation to define the curve to be the integral over this given a curve of vectors that we had. And now, again, you can check, you just like go through now this proof that we had, or the construction, and you calculate the Frenet error frame of that curve and check that the Frenet error frame given by this curve that we just constructed. So essentially, you calculate what the equations are for the Frenet error frame using this equation, like what we had, like the construction, and you pop out after like a very simple calculation that these ones are given by T, N, and B, using that these ones are orthogonal. So that means that T, N, and B, which were like satisfying this equation, which I just erased, shows you also that automatically that the curvature and the kappa and the tau, the two functions that we started with, are indeed curvature and torsion. Because they satisfy exactly the same equations that the Frenet error frame was by construction. So kappa and T are indeed the curvature and the torsion of the curve. So that means by this construction we got our C of T. So to recall, what we did was we like took these Frenet error equations that we derived earlier as the definition of T, N, and B. And then once we found T, N, and B as a unique solution to these equations, we just defined the curve C as the integral over the T. And yeah, once we have that, then we checked using these kinds of two calculations that the Frenet error frame and the curvature and torsion of that curve are indeed what we started with. Yeah, so that's like the main result for this first part of the class today is that up to fixing like these constant in the starting point, it means that once you have the curvature and the torsion of a function, you essentially know the curve. So that's like the important result here. Okay. So the first, I want to make some remarks about this theorem. The first one is it's something that might like look very confusing to you at first. Is that in order, like, if you have a curve, it has like at each point it has 3 degrees of freedom, right? Like if I have something in 3 dimensions, it can like move it in 3 different dimensions. So intuitively, if I need to describe a curve, I need 3 functions of time in order to describe its behavior in space. But what we saw here, it looks like we need to give 2 functions. Right? I only need to give 2 functions of time, namely kappa and tau, and some constants, in order to describe the curve. So where's the third information, like the time? Like I need like one more function of time in order to fix the third coordinate. Do you have some idea where the third function of time is hidden? It's quite like here's one, here's the second one, and the third one is like hidden there. What we had like given is namely that the curve has to be unit speed, and that says that like the speed of the curve has to be the constant function 1. So that gives us like one more function of time, namely the constant function of 1, that has something to do with the curve. So essentially, we not only have given like 2 functions, but like 3 functions. So that makes sense that in order to describe a curve in 3 dimensions, which you need like 3 functions for, we are given 3 functions, just like one of them happens to be the constant one. Like the easiest way would be to say like if you want 3 functions, you just take each of the components as one of the functions. So that would be we have 3 different kind of functions. One of them is saying the x, the y, and the z direction. And as I said, like the 3 functions that we have are kappa, tau, and essentially the speed of the curve, and this one is constant equals to 1. So you could reformulate the whole theorem and actually put like a third curve in here and say that should be the speed of the curve. So that would be maybe one way to make it more clear that we really have three curves, would be saying like, let's give ourselves some function which actually takes values like somewhere in the unit sphere, and then we would replace here the unit speed with like the speed v. So that's just like happens to be a constant function. So that's like one remark, that it's like really consistent. And the second remark was about this assumption that we started with a curvature equals to which is positive. Because we wanted to say something about so that's like mostly saying that like this assumption is not, in some way it's not perfect, because for example if you say like the curvature has to be 0, you can also solve that equation. It's just like very hard like to say something in between where you have a function of the curvature which sometimes has a 0, because then you don't know really what happens there with the normal derivative and stuff like that. So that's why we assume that the curvature is positive in this theorem. But sometimes, like you can definitely construct curves where the curvature has zeros at certain points, and then this theorem is not like directly applicable to reconstruct such curves. So there's something in between, like you have the full generality and these assumptions of the theorem, but which are mostly conceptual, because we need like this zero frame. All right. Okay. Do you have any questions concerning curves and this proof? Okay. If that's not the case, then I think we go into the break now, and resume in 15 minutes or 20 past 7. that's okay. Yeah, first, switch off the microphone. So that's the problem with like some of you have like not the background to understand all of the things that I talk about. That's okay. If you like sometimes, for example, this ODE theorem is like new to you. Either you accept it as a black box and say like, okay, there is a theorem that I've never heard about that says something like that, but it's not really that essential that you really follow any of these steps. So it's okay for you to sometimes say, okay, I've not heard that, but it's also not really the most important thing, like that there is this kind of thing. So I'm trying to find like the balance between that you understand most of it, like you should understand the content like of the theorem, what it says, what were the assumptions, but maybe not like all the steps in the theorem. So that's okay. So you struggle sometimes with certain mathematical arguments. Yeah, so it might be like a bit different to like some other classes where you really have like everything like well defined and you knew everything. So that will sometimes happen is that like certain things you have not seen before, and then you like either you look that up and like you do a bit of like research and like look up like what is this theorem about ordinary differential equations, or you just accept that it's not like super important. Yeah, like in this case it's not super important. I would not spend too much time. If it's like at some point gets too advanced and you can't follow because there's too much things from analysis or stuff like that, then please just like let me know. And I try to give you more background or if you have some more reading material that you can learn this thing on your own. Does it work? You still look a bit confused.
Yes, understand some concepts. So we will search some information on some theorems we didn't have that.
Yes, well, it's totally okay to just say it. Like if I say like there is a theorem that tells you that, just treat it maybe as just okay, there is this theorem, but you don't have to know that theorem in itself. So maybe at some point you will realize like later you have that theorem and then you say, that was the theorem that like this professor in differential geometry talked about. But like just like sometimes accept that certain things are like coming from a black box. Not everything is like really
So we need to know about how we get it, but how we use it.
Yeah, so like that's like I'm trying to do is what you should definitely always do is like solve the homework equation, like homework exercises. So these ones are really the most important thing. You can't follow some of the proofs in the class, that's okay. But what you should really be able to do is like solve the homeworks and like really just focus on that. And then if you have like more time, then you can look up what this theorem was. Okay, let's continue. So actually we almost concluded the first part of the whole lectures, which were about curves. And we can now move on to surfaces. But sometimes we will, like the nice part about curves that they will come back at some point. Namely, one of the interesting ways to study surfaces is by looking at how curves move on the surface. So that will be one particular instance where we will talk about curves again. But now we would like to look at surfaces, and I would need to define first what is a surface for you. With curves, we had like two different perspectives. One was that like it was really just like an object in 3 dimensions, and the other one was that you can really think of that as a particle, right? Where it's like a particle that starts here and slowly travels along the curve. And then you think more of a curve in 3 dimensions more as like a path. And this path of a particle was really good because it, like this perspective were really helpful because it allows us to talk about like the tangent vector, the velocity, the speed, and the curvature of things like this. So we would like to use the same kind of strategy to study surfaces, where we would like say like instead of looking at the surface like this, where it's like a bottle and like you can really think of that as a three-dimensional object, we would like to have kind of like some way to do a calculus in it. So we need like some kind of coordinate systems. And the way we do that is like, we can think of that as like an abstract coordinate system. And then what we do is like, once you have that object, you kind of put these coordinate systems on it. So you just like have some way of like endowing your abstract surface that you look at with like some kind of coordinates, where you say like in a certain direction it's x and y. And you will already see it, like on a simple example of like the cylinder, there will be some kind of problems maybe at some points, where we have to think about what happens if the coordinate system comes back to itself. So you need like some way to make these kind of consistent choices. Like what happens if like, if I say this one is 1, and then I go 1, 2, 3, 4, and then I'm back to 0. So there needs to be some kind of like, way to make these kind of choices in a more like consistent way. So these are the kind of problems that we face when we define what a surface is. So the easiest way, and that's what we study today, is like what is called parameterized surfaces, which is essentially you take a sheet of paper with some coordinate system and you do something like that, where you just like roll it a little bit. You have like no problems with like that they have to touch itself, so like just like something that is like curved in space, but not like something that like intersects itself again or something. So like very like in somewhere like a coordinate system which is like a bit curved. And that's what we call parameterized surfaces. And that's the like the things that we look at today. And the similarity is that for curves, we were thinking of them as something that has defined on, say, an open interval of the real lines. And then given that, we can assign that a certain curve, and the function then, of course, tells you where you are in the space. So on surfaces, you need to be more precise. So now we have like something, but there's something that the coordinate system lives on R2, right? Like it's like I need two kind of information, like two-dimensional information to describe a surface if I want to curve it. So the information that we are given is like already something in 2 dimensions, and then we have like a function which is usually called phi, which describes how that one is like bent and how it's curved in some way. So that's described by phi. So that's like the rough idea. It's like to consider surfaces as something that is like nice and square, and then have a map which is phi, which turns it into something curved. Similar like how we imagined like a curve to be a one-dimensional thing, and then this map C is turning that one into something that is curved. So now we have to like talk about certain properties of these maps. So for example, with a curve, we say that this map has to be smooth. So we didn't want it to have like kind of like really strange curves. So similarly, we don't want to study things that are really like where you like rip the surface in parts or something like that. So this map has to be also smooth. So some of you might have seen already what it means for a function to be smooth, but like I will recall that a little bit more detail. And like similarly here we had like certain regular curves. Almost all things that we talked about needed like the regularity because at points where like the velocity were not defined and or like 0, then there was not much geometry happening. And same way here, we would like to to say some kind of regularity for the phi, which in some ways is like for a curve, regularity means that you move always, which means you're not like a one-dimensional object, right? Like you always have like a tangent direction where you move into. And similar here means that like what is not allowed to happen is that you have like your two-dimensional thing and you curl it to something that gets smaller and smaller, and at some point only has like one dimension left. So actually, so that it's, I can't really do that. Like, but I think you get the idea that like you have like something which is two-dimensional originally, and which then at some point like you curl it so far down that it's actually only one-dimensional, or it just contracts to one point. So we would like also to have things like this like not happening, because we would like to really talk about some two-dimensional objects and not like something one-dimensional just parameterized by 2 points. So that's like the next objective. And I would like to start by recalling or giving some definition, depending on your background, about smoothness in differentiability. In higher dimensions. So just like for curves, we used here, say like some subset as the parameter. And in 2 dimensions, I will mostly write like x and y as the parameters. Or sometimes x1 and x2. So just like for to set the stage for notation. And the first thing is what we need to do is we need to find a replacement for the interval. So here, to something that is higher dimensional. And the correct notion of that is openness of subsets. So let me recall some of the definitions around that. So we have an open bore, or actually it's like a bit of a misnomer, and it should be more for a disk. With center a certain point P, which we say is P1, P2, in radius equals bigger than 0. So we would like to say what is like a small disk around a point, and just intuitively, all these points for which the distance between the original point of the given point is strictly smaller than the radius. So the picture really is what you would guess. So we have some point P here, and some radius R, and then this everything inside here is then the bore of radius P. So that's just like definition, or just like as a name. And then we say that the subset, let's call it D, in R2, it's called open if each point say P of D has a ball which is contained. Like we say that the subset is open if like every point in the subset has like a small ball around it, which is like again in the subset. So two examples is, or like the picture in itself is something, you have your subset D here, and you choose a point P, and what you try to find is a small ball around that point. Which is again completely contained in D. And examples, for example, D, that's like the standard example, is like where we just have open interval of both of like a rectangular essentially, where the x has to be between E1 and E2, and the y has to be between E1 and B2. And the point here is to say that this one is really like open, the open interval, that's why it's called open. So this one is open. But if you replace that with the closed interval, and the problem here is that if you're like on the boundary, say you are like at this point there, and you try to find, you would like to say that it's now open. So what you need to do is then at that point you need to find a ball of some radius so that the ball is completely contained in this rectangular. But you see, regardless of how small you try to do that, even if you take like only a tiny little ball, there's always some part which is outside of the rectangular. So that's why like the closed interval where you have like these boundary points to be part of your D, these ones are not open, but like the ones where we exclude these points, like even if I take some point which is relatively close to the boundary, say here, some point here, I can always find like a very small ball around it, so that it's completely contained in my set. So that's why the interior points are nice, but not the boundary points. So in some way, maybe that's like the best way to think about like open subsets are these things where we don't have a boundary contained in the set. where the boundary is like something outside, like where you draw it, and then the inner points are really like nice points, and the boundary points are something that is not part of the set. Yeah. The standard example is really keep that one in mind. Really just think of that as a rectangular, like this one, without these outside points. And the reason why we need like this this whole discussion of open sets is because we want to talk about taking derivatives, and the idea of taking derivatives is that we change slightly our point, and then like say our map, how the map is changing. But if you have like a map which is defined like on the closed interval, we can't say, like we can't vary in this direction downstairs, because there is just like no longer defined our function. So that's why we need something that is defined on open sets in order to talk about it being, to say that something is smooth or not smooth. Okay, so let's talk about differentiability. So we have a continuous map or continuous function, which is defined on some open subset. And it takes values in here. And we usually write this one as phi of x and y equals to a certain function in each of the coordinates. And we would say that this one is smooth. So the way we do that is by smooth means that if I have a point here, and I take like a different point which is relatively close, and then I put them under my map, which I get like a different point here, and I get a different point here. And smoothness essentially just says that these 2 points, which if they are like staying close together in this in this subset, then they also still close on my surface. So that's the important part, is that like I don't rip apart like this piece of paper, right? Like for example, if I would like have that as my original coordinate system, and then I rip them apart, then some points which would be I don't want to do that, but so if you have like some points and you rip it apart, then like some points which would be close together in here, and then like on a different size of the rupture would be like very much far apart from each other after I ripped it apart. To show you that, like these 2 points are like very close to each other, right? Like on that side and off that side. So after I rub it, then these points which were originally very close to each other are like very apart from each other. So that's why it's things that we don't want to happen. Like we want like things that are very close, or in our original coordinate system should be also very close on our surface. So that's why we need to talk about smoothness. And the way we do that is essentially by reducing it to smoothness of the curves. So what would like to say essentially is like we choose some kind of curve, and then this curve connects these 2 points. And then what we say is that this curve, which are like connecting these points, should be also still smooth in our original setting. So that's the idea. So this one is continuous differentiable, or it's called sometimes C1. If for each point on P in here, and open bore which is like contained in here, the max should be a C1 we define 2 curves, namely C1 of T, which is just changing the point in slightly in the x direction, and the second curve just only changing things in the y direction. If these ones are smooth in the sense of what we just talked about at the beginning of the lecture. So the idea is again that you have essentially you look at like these red lines and the black lines. That one of them would be this one, the C1 would be like going something in the x direction like this, and these ones would be something that goes like in the black line. And then you look at like how this map is like changing them, and you look at that these curves, which are now defined as something that lives in 3 dimensions, if they are still smooth in a sense. So that's the definition. Similar, you can say like that something is smooth if these maps down here are smooth. Yeah. And then we need like the partial derivatives.